Welcome to Q Point. This is our second lecture on analog circuits. In this lecture, we discuss the characteristics and properties of intrinsic semiconductors. From the first lecture, we have seen that to have a thorough understanding of analog circuits, it's desirable to have a basic idea of the behavior of solid state devices. These solid state devices are made using semiconductor materials. Semiconductor materials are materials whose conductivity lies between that of metals and insulators. There are two types of semiconductors: single element semiconductors, compound semiconductors. Compound semiconductors are used for special purposes. We will be discussing elemental semiconductors. Germanium was the first semiconductor used for constructing electronic devices. Soon, silicon replaced germanium because of two reasons. One reason is silicon is abundantly available in nature, and the second reason is silicon devices have low sensitivity to temperature than germanium devices. So silicon is the most widely used single element semiconductor. So our discussion is mainly about silicon devices. In lecture 1, we saw that the conductivity is proportional to electron concentration. For a good conductor, the electron concentration N is very large, of the order of 10 raised to 28 electrons per cubic meter. And for an insulator, it's very small, of the order of 10 raised to 7 electrons per cubic meter. For a semiconductor, N lies between these values. The most widely used semiconductor is silicon, and so we will discuss silicon devices only. The electronic configuration of silicon is 284. So there are 4 electrons in the valence shell. The three-dimensional structure of silicon consists of regular repetition of a unit cell having the form of a tetrahedron with an atom at each vertex. A pure semiconductor in which no impurities are added is called an intrinsic semiconductor. An impurity means anything other than silicon. We can develop a symbolic two-dimensional representation of the crystal structure of intrinsic silicon as follows. Consider a single silicon atom. In the figure, it is shown, the valence shell is shown, and the inner circle represents the core, which contains a nucleus and all the electrons except the electrons in the valence shell. Since there are 4 valence electrons, the core has a charge of +4. Now consider 4 neighboring atoms of this particular atom. We are focusing on this atom. It has 4 neighboring atoms. In order to attain a stable configuration, this atom shares one electron from each of the 4 neighboring atoms. So the structure will be like this. So this atom now has a stable configuration. Similarly, each silicon atom has 4 neighboring atoms, and this process of sharing of electrons continues. The valence electrons serve to bind one atom to the next, and this results in these electrons being tightly bound to the nucleus. This type of bond between atoms in which electrons are shared is called a covalent bond. The valence electrons in a semiconductor are not free to wander about as in a metal, but they are trapped in the covalent bond between atoms. Electrons can be freed and can be made available for conduction if it is possible to break the bonds. So if you supply sufficient energy to break the bonds, we can make electrons free. The minimum energy required to break the covalent bond is known as the band gap energy, Eg. The value of band gap energy for silicon is 1.12 electron volts. 1 electron volt is 1.6 into 10 raised to minus 19 joules. At absolute zero temperature, the covalent bonds are intact and no electrons are available for conduction. So at 0 Kelvin, silicon behaves as an insulator. But as the temperature increases, say at room temperature, some covalent bonds are broken because of thermal energy and some electrons are made free for conduction. Figure shows one bond is broken and one electron from this position is freed, and this electron is now freely available for conduction in the crystal structure. The energy to detach this electron from the nucleus is very small, of the order of 0.05 electron volts. So this electron is free to move. And you can see that when an electron from a broken covalent bond is moved to the crystal structure, a vacancy of an electron is created at the original position of the electron. This vacancy is called a hole. Electrons and holes are generated in pairs. We say that an electron hole pair EHP is generated. At room temperature, more covalent bonds are broken and a number of electrons are freed for conduction. It is likely that an electron from a broken covalent bond moves to a hole. See, there are other covalent bonds broken. Assume that this is broken. From this broken bond, an electron may move to the crystal structure, or it is likely that this electron may move to another hole. It may happen. So when it moves to another hole, that original hole disappears and a new hole is generated at the position of the electron. So even though the electron is moved from left to right in this case, it appears that the hole moves from right to left. The hole effectively moves in the direction opposite to that of the electron. This new hole may be filled with another electron from another bond and the process repeats. This process repeats, resulting in a conduction of electricity which does not involve free electrons. So here you can see a conduction. Here also the charge carriers are moving, means there is a conduction. But in this conduction, there are no free charge carriers available. Free electrons are available. The holes are actually moving. Free electrons are here. In this conduction process, free electrons are not taking part. The hole behaves as a positive charge equal in magnitude to the charge of an electron. We can consider in all respects that the holes as physical entities whose movement constitutes electric current. Thus, current in a semiconductor has two components. One is the current due to hole motion. We designate this as IP. Suppose IP is in this direction, hole is moving in this direction from right to left. And a second component due to the motion of electron, we call it IN, which is opposite to the direction of flow of electrons. Electrons are moving from left to right. The current is in this opposite direction. So both the currents are in the same direction and the total current is the sum of these currents. Electrons and holes are called carriers of electricity or simply carriers. Now we will calculate what is the concentration of electrons or holes in an intrinsic semiconductor. Electrons and holes move randomly in the crystal structure. In this motion, some electrons may move into holes. See, earlier we have seen that an electron from a broken covalent bond may move to a hole. Now we discuss another case. A free electron may sometimes move into a hole. Under that situation, both the holes and the electron will disappear. This process is called recombination. See, consider this. Assume that this electron is moving to this hole. So this electron vanishes and the hole vanishes. Electron and holes are disappearing in pairs. Thermal generation and recombination of carriers is a continuous process. So a number of thermal carriers are generated, number of covalent bonds are broken, number of electron hole pairs are generated, another number of electron hole pairs are disappeared. So this process continues, and at thermal equilibrium we can write N equal to P equal to Ni. The electron concentration is equal to the hole concentration, and this concentration is known as the intrinsic concentration Ni, or we can write N into P is equal to Ni square. This is an important relationship, and this relationship is known as the mass action law. N into P equals Ni square. Ni strongly depends on temperature. As temperature increases, more and more covalent bonds are broken. So that will increase the intrinsic concentration. Ni is given by this expression. Ni is equal to B T raised to 3 by 2 e raised to minus Eg by 2 kT. The values are given here. Substitute these values and calculate Ni at room temperature. Room temperature is taken to be 300 Kelvin. We get Ni is equal to 1.5 into 10 raised to 10 carriers per cubic centimeter. We may think that this number is very large and silicon is a good conductor, but that is not true. Compare this with the concentration of silicon atoms at room temperature, which is 5 into 10 raised to 22 atoms per cubic centimeter. This value is negligible. So if you divide these values, you will get, we see that at room temperature only one atom in 3 into 10 raised to 12 is ionized and contribute to a free electron and a hole. So only one in 3 into 10 raised to 12 atoms contribute one electron. Remember, in a conductor, 1 or 2 electrons per atom are available for conduction. So at room temperature, silicon is not a good conductor. Moreover, Ni, the intrinsic concentration, and hence the conductivity of pure silicon are strongly dependent on temperature, which is not a desirable quality. Because of this, pure silicon has no practical use in circuit design. Later we will find how silicon can be used in circuit design. Now let us find an expression for the conductivity. In a semiconductor, two types of charge carriers participate in conduction: negative electrons and positive holes. In a metallic conductor, the current density is given by J is equal to sigma E, where sigma is equal to Q into N into mu. We observed this fact in the first lecture. In a semiconductor, since both electrons and holes contribute to current, we have to take the mobilities of electrons and holes into account. Electrons have higher mobility than holes. Why do electrons have higher mobility than holes? We will discuss that later. Denoting electron mobility by mu n and hole mobility by mu p, we can write for a semiconductor a conductivity sigma equals Q into N mu n plus P mu p per ohm meter. For intrinsic semiconductor, N equal to P equal to Ni. So this expression now becomes intrinsic conductivity is sigma I equals Q into Ni into mu n plus mu p per ohm meter. You can see sigma I. When you calculate the value of sigma I, you will be getting 4.35 into 10 raised to minus 6 per ohm centimeter. Now another method of representing a semiconductor material or any material is by using energy band diagram. So we will now plot the energy band diagram of a semiconductor. We already have seen that in silicon it takes a minimum of 1.12 electron volt of energy to free an electron from a bond so that it can move about the crystal and conduct. To visualize this, we draw the energy band diagram. The energy band diagram is a plot of electron energy versus the number of allowed energy levels. Allowed energy levels. By Bohr atom model, you know that electrons can occupy only certain allowed energy levels. In an atom, electrons are distributed in various shells and possessing different energies. Electron energy increases as shell radius increases. The energy band diagram shown here corresponds to the valence band, and the energy band diagram corresponding to inner core electrons are not shown here. The diagram consists of a valence band at lower energy levels, conduction band is at higher energy level. So it consists of a valence band and a conduction band separated by a forbidden energy band or a band gap. EV corresponds to the top of valence band and EC corresponds to the bottom of conduction band. EV plus the forbidden energy gap is equal to EC. The electrons in the covalent bonds are in the valence band. Electrons free to conduct are in the conduction band. The conduction band electrons are at higher energy levels and separated by the band gap energy Eg, separated from the valence band by the band gap energy Eg. Eg is equal to 1.12 electron volt for silicon. Electrons cannot exist within the forbidden energy band. EC is the bottom of the conduction band and EV is the top of valence band. EV plus Eg is equal to EC. At 0 Kelvin, the valence band is completely filled with electrons and the conduction band is completely empty. So there are no charge carriers available for electrons available for movement in the conduction band, and all the allowed energy levels in the valence band are filled. So there are no motion of electrons in valence band either. So at 0 Kelvin, silicon is an insulator. But as temperature increases, at room temperature, due to thermal energy, some electrons are excited into the conduction band. Some will be excited into the conduction band. This figure is only a schematic diagram. So there are a number of electrons now available in the conduction band and equal number of holes in the valence band. You can see that the conduction band is still almost empty. Many of the allowed energy levels are empty here. Whereas you can see that the allowed energy levels are almost filled in the valence band. The electrons in the conduction band are in random motion. And in their motion, they collide with each other and some of them will lose its energy. And when it loses energy, it comes back to the valence band. But when it comes back to the valence band, it can move only to a vacant position in the valence band because the other energy levels are filled. This process is the recombination that we already have discussed. At the same time, some other electrons in the valence band may be excited to the conduction band. So this process of excitation to the conduction band and coming back to the valence band, recombination, this process continues. This process of excitation and recombination is continuous, and at thermal equilibrium, there will be a number of electrons in the conduction band and an equal number of holes in the valence band. This value is Ni, the intrinsic concentration. Now, under this situation, assume that we apply an electric field in a direction shown here from right to left. This is the direction of electric field. In the conduction band, electrons will move. See, when we are applying an electric field from right to left, electrons will move from left to right. Electrons will move in the direction opposite to the direction of the field, resulting in a current In from right to left. The direction of current is opposite to the flow of electrons. So electrons moving from left to right will constitute a current In from right to left. This is in the conduction band. Now in the valence band also, electrons move from left to right. It can move from one position to a vacant position, that is to a hole. So when an electron moves towards the right, it appears that the holes are moving towards the left. Electrons can move only to a vacant space, that is to a hole, because all other allowed energy states are filled. So when an electron moves to the position of a hole, the hole disappears and a new hole is created at the original position of the electron. Thus the hole moves to the left, resulting in a current Ip from right to left, as shown here. So there are two components of currents, In and Ip. And you can see that the electrons are moving in the conduction band and holes are moving in the valence band. So the total current I is equal to In plus Ip. Note that the electrons are moving in the conduction band which is almost empty. There are many places, many allowed energy states vacant, while the holes are moving in the valence band which is tightly packed. This means electrons are more free to move than holes. This is the reason why electrons have higher mobility than holes. You can see in the table that the hole mobility or electron mobility is approximately 2.5 times the hole mobility. It is because of this reason that N-type devices are preferred over P-type devices. Say we have NPN transistors and PNP transistors. We will study that later. In that, NPN transistors are popularly used than PNP transistors. N-channel FETs are used more than P-type P-channel FETs and so on. It is because of the higher mobility of electrons. Higher mobility of electrons means these type of devices will have better high frequency response than P-type devices. This is the reason why we are using N-type devices. Now we will recap the important points. A pure semiconductor without impurities added is called an intrinsic semiconductor. Silicon is the most widely used elemental semiconductor. In a semiconductor material, atoms are held together by covalent bonds. The minimum energy required to break a covalent bond is known as the band gap energy Eg. Eg is equal to 1.12 electron volt for silicon. A vacancy of an electron is called a hole. It can be treated as a positive charge. The mass action law states that N into P equal to Ni square at thermal equilibrium. The intrinsic concentration of silicon is 1.5 into 10 raised to 10 centimeter cube is very small compared to the concentration of silicon atoms, which is 5 into 10 raised to 22 atoms per cubic centimeter. Electrons have higher mobility than holes. These are the references. And thank you.